You're live. Go ahead.
Hey, everybody. Welcome to another edition, the first Thursday edition of Gruber Wired Hour. I'm Mark Beach.
I am John Dotson, and thank you once again for joining us today.
Yes. So, pardon our technical difficulties. You know, it's raining in Phoenix, so that causes problems.
A little bit of an issue. So we thought that we would pay a tribute to spring training since they had to, shut the games down for a little while. So we took a bit of a break just like they did.
That's it, man. You know? I mean, we got to do what we got to do.
Yeah, no, speaking of rain, it does rain here. We got a nice rain in this afternoon. Phoenix annually gets only maybe about 7.5 inches of rain every year. So we'll take every
had
drop.
to go across Gruber Lake to get here today.
I know. It's true. We get quite a bit of rain that puddles up outside there.
We do,
so we get wet feet.
Wet feet.
Speaking of wet feet, I got to tell you, look what's happened to me. I really can't believe it myself. Suddenly, you're on top of the world. And I had this Super Bowl bet with Terry, right?
Right.
And,
anyway, you won that bet.
I won the bet.
Yes.
And the bet, the winner was...
In your face.
Yeah. But anyway, what I won was a bobblehead.
Yep.
And Terry had a very special bobblehead, actually handmade and handcrafted for me of Taylor Swift.
Uh-huh.
It should have been somebody else, but, believe it or not, I'm walking on air. Terry, thank you.
Can't hear that. I need something hard on here so when I bang my head against the mic.
I never thought I could feel so free.
Yeah.
Flying away like a wing in a prayer.
I know you're referencing Taylor Swift songs, but sorry for you Swifties out there. I don't listen to it.
It's not Taylor Swift.
Oh, okay.
Okay. Yeah.
Oh.
It is a theme song to the greatest American hero. Remember that?
Flying away on a wing in a prayer. Yeah. Oh, yeah.
Yeah. Yeah. Very good stuff, huh?
Believe it or not, it's just me.
Just me and Taylor Swift.
Yes. So you are the Swiftie today.
The Swiftie. So today we're going to get into something a little bit different. It's kind of cool stuff.
It's really fascinating. So a little backstory on this. Harry, we were in our pod area, and he was talking about a customer that needed some cables to be able to last in liquid.
Yeah, and specifically a dielectric liquid.
Right. Well, we didn't go into that at first. He just said, they were getting all brittle and everything. And I'm like, what's it connecting to? And he said, oh, they're building all these mining machines for crypto, or they have them, and they're, the graphics cards are in liquid cooling. And I'm like, in liquid cooling? And so I thought he was gagging me, right? Yeah. I thought he was pranking. And I'm like, no.
Yeah, because liquid cooled is a bit of a different setup.
Right. It goes against everything you think to think, I'm going to put a computer card or a whole computer in liquid.
Yeah.
But I guess the only thing that matters is, does the liquid conduct electricity or not?
Yeah, and the thermal capacity of the liquid itself.
It's greater than air by like 30, 40 times, I think. So its capacity and then the ability to be precise with circulating and getting it back in is,
Yeah, and this stuff started way back in the 18th century?
That's,
to be honest with you, the beginnings of really taking a look at using liquid to submerge equipment in and cool it.
Right, exactly.
And
by the way, just so everybody knows, this is a new day and time for Gruber Wired Hour. So just make sure that you tune in every Thursday at 3 o'clock.
3 o'clock.
Arizona time. And all y'all, this Sunday, you change time zones. We don't. Or we change time zones. We don't change time. Our clock doesn't change.
No, we don't move at all.
We're going to become the same time as California again.
We're normal compared to everyone else.
We just don't, buy into all the hype.
No.
So, hey,
you can't say we're normal when we're the same as California.
No. They change their clocks. We don't. So we'll be on the same time as them, but not on the same plane.
Yeah, we're normal.
Yeah. We just, it's another day. We just wake up, and you know what? 24 hours is 24 hours for us. Not for some people on Sunday.
True.
Yeah.
For us it is.
For us it is. Yep.
So this immersion cooling, I mean, it started all those years ago, and it's
Yep.
kind of developed and worked its way through. And it wasn't really, as I did my research on this, really coming to light until we get into crypto and mining.
Right.
And that really brought this to a head of being able to take, just because of the machines that are needed and the amount of heat that needs to be dispersed in order to mine these cryptos.
Right. It really improves productivity of the machinery and lifespan too. As you can imagine, they don't dry out, but there are challenges associated with that. And when I started looking into this after Harry brought it up, there are boards of people who have studied and analyzed all the different materials that can exist in these fluids. So, there's ester-based liquids and fluorocarbon-based liquids.
Yeah, Jesse, if you could pull up photo number 2. And while he's pulling that up, Pete makes a great point that it's the automotive world that really taught us a lot about liquid cooling.
Sure.
As a transition into where we are today.
Right. It's such an efficient medium for dispersing heat. And so that's there we go.
Yeah, here we go. This is the chart of dielectric liquid.
Right. So depending on the type of material that's used and the makeup of the cabling, there are a couple of problems that can happen. One is that the cabling can leach its own chemical compounds into the fluid, which makes the cable brittle. The other challenge is certain materials that will absorb the liquid and become expanded. It will expand and create tightness on the inside of the cable.
Yeah, all causing disruptions.
Right.
And so it depends on the fluid that's being used, like you see in the chart here. You look at the properties, and that's really what we're taking a look at, is those different chemicals and properties that they have, and how do they dissipate?
Right.
The heat radiance is coming off, and also how does it transform the flow of actual energy?
Right.
There's some fluids on this chart that there's no energy transfer whatsoever.
Right.
So there's no issues with any sort of shock or anything like that taking place.
Well, and you think about it, when you're in an air-cooled environment, the heat source is, it's dispersing into the air. So, attached cables that are near it are not as affected by that as the individual unit. But in this particular environment, all of the fluid heats up.
Yeah.
Okay, as it's dispersing it. So the challenge too is having a cable that can have heat tolerance as well. I think the rating is somewhere around 80 degrees Celsius. And remember, it's constant.
Yeah.
Right. As opposed to airflow, which can create fluctuation. That's what I meant by liquid cooling being more precise, because it is the same temperature throughout, and it just pulls it out and then gets routed through a cooling system, and it drops it by 20 to 30 degrees Celsius, gets recirculated back in.
Yeah, and we can see this, and if you could pull up photo number 5. And what you're talking about is there's 2 types of phases in this cooling process. You have a phase 1 system.
Right.
And in the phase 1 system, what you have is the coolant is all self-contained, and it comes out of into a heat exchange,
Right.
and then back into the what am I thinking of?
The tank.
The tank itself.
Yeah,
Yes.
right.
And so that's a phase 1 type system.
Right.
And it constantly is running and reverberating and constantly just continuously, rotates the water through the system.
Right.
Phase 2 in that aspect, as you can see, I believe in this one here,
Yep.
You get as kind of a
It's like a 2-stage evap cooler.
exactly.
Right.
You get
So you
evaporation.
get 2-stage cooling that takes place in there. Yes.
Yeah. So you have those 2 different types of systems that are being used right now.
Right. And so some of the benefits of doing cooling like this is, can you imagine? So I'm sure we've all seen YouTube videos going into mining operations where the GPUs are running, and, you know, mining Bitcoin, they are noisy.
Very noisy.
This dampens the noise immensely.
Yeah, and picture number 4, we can actually show this. This is actually an actual setup of a Bitcoin mining operation that somebody had put in place. And so, like you said, it takes away the noise. There's a lot of factors. Here we go. You see each individual case there.
Yep.
Then you have the cabling going into it. And what do you notice you don't see? You don't see a lot of fans.
Right. Right, because all the stuff is happening inside the liquid.
Correct. And so at that point in time, you're also talking about not only saving space within your system, right? You're talking saving energy as far as not having a need for air conditioning, cooling.
Right.
So they're much more effective and efficient in that aspect.
Right. You know how cold server rooms are and everything like that. Well, this eliminates this eliminates that need. And you know, one of the topics that we talked about at our last show, so a week ago Monday, was density as being part of, you know, the technology, edge technology, right? Being able to get more data going through smaller conduits, more data being able to get handled in data centers. Well, this promotes density as well, because now you don't have to be sensitive with how many units are in a room and how much that room heats up, and, you know, how many air conditioners you have to have on there to support that. This takes care of it all.
Yeah, and so a setup like this, you can actually, since you're saving that much space, you can see the expansion ability that you do have. So you have more compact computing taking place, but yet you're able to expand around that with the amount of computing that can take place.
Right, 100%. And, you know, just while we're here, like, subscribe, and share this podcast. We value you guys as customers. Feel free to write questions on here for us. We'll be glad to answer them live. And let's roll on.
And yeah, Daryl just popped up. AI processing demands are also driving more efficient cooling methods, and that is so true.
Yep.
Because AI is going to be pulling a lot more computing.
Right.
I mean, it's just getting more dense as far as that goes. So you're seeing a heating up taking place at a lot larger scale.
Right. Right. And you know, so this is just a really amazing technology that I've continued to dig into as I've been here at Gruber, and the idea that it not only, because if it's cooling more efficiently, right, and it's a broader spectrum cooling, or it's cooling everything down, it's also going to extend the life of the equipment.
Sure. And that's another thing to talk about too, because what you end up is there are some challenges with this. Speaking of equipment, initially the investment and startup cost is going to be a little bit more than you probably would think of or expect.
Right.
But over a period of, you know, a long period of time, you're saving that money in efficiency.
Right. It's like spending more money for a hybrid car or an electric car, but not having an expense for gas.
Yeah.
Right.
And, you know, just like you changing your oil in your vehicle, you just can't take your oil and pour it out in your yard.
Right.
So same thing with this particular types of coolant and dielectric liquids. You just can't take and dispose of them that easily as well.
Right.
So there are places you can get that taken care of, just like the oil in your vehicle. So it is more transparent and more convenient in that aspect.
Right. And just, you know, getting over the idea that we're dropping a computer into liquid, that's a pretty
so nobody go
that's
home.
A paradigm shift. No, don't
go home and take a bath and take your laptop with you.
No.
And
no,
not gonna
it
work.
has to be special liquids, and dielectric just means it doesn't conduct electricity.
Correct.
Right.
Or it does at a very minimal stage.
Right.
You
so
know,
you don't have circuits short circuiting and jumping.
Correct.
Arcing.
You know, and you were talking about the cabling, and I brought up the sheet here with a lot of the cabling. You got PVC jackets, and then you got PE, polyethylene. All these different jacket types are out there to handle these harsh environments. So when you're going into a system like this, you really need to pay particular attention to what type of cabling and cabling jacket that you're using.
Right, and there are open source materials out there from some of these committees that have studied different cooling liquids and materials, because it's not just data cabling in there. I mean, you've got gaskets, and you've got the components that make up a circuit board, and you've got, you know, anything that goes. You look at the wires that jumper on circuit boards, and you understand that there are so many different things that you have to consider.
Oh yeah.
When you're building or dropping these in, right? And so some of them are and cabling was one that was a problem we needed to solve. And we looked at harsh environment cabling because it can handle high temp,
Sure.
and it can handle exposure to oils and things like that. But the real challenge is, can it be submerged? Because we're talking about harsh environment is incidental contact.
Sure. But
And
constant is a different story.
Right. And I know that in talking to some chemical engineers about this, because we're still going down this road with this, some of the studies with the polyurethane, in some fluids it's okay, in other fluids it's going to leach and become brittle. With one solution that we're hoping to look at right now, and I've reached out to a few sources, is dealing with basically Teflon.
Sure.
PTFE
Yeah.
is as the jacketing material. And right now, Teflon is used more inside the cable than it is outside. So, but there are a few people that manufacture with the PTFE jacket.
Yeah, but don't they cover that also with a thermoelastic rubber compound?
Right.
So that's something I've been learning about more and what's out there.
Right.
And so you're starting to see a lot more of these thermoplastics take place in this because there's a need for them.
Right. And you're dealing with not just the cable itself, but then also the boots and the jacks, or the modular plugs.
Yeah, this is something, like you said, there's so many different moving parts and pieces that you have to take that in consideration.
Right.
So you got to take a look at the mod plug. You
Right.
know, what compounds are in that? How is it seated up? Is there any leach into the cabling itself?
Right.
Sometimes you have a need for a molded situation, which I think is the need that Harry had to take a look at.
Right. Right. Yeah. And so boot molding, just to kind of seal things up. Not that there's going to be any issue with the electrical side of things, but just from a breakdown of the internal jacketing and deterioration of that sort of thing. So it's hugely important. And these documents that are out there, very informative, talk about all the different fluids, and then the ratings for each material, each jacketing material, for cabling, but it also talks about component materials within the assembly of a computer in order to determine whether those materials have been tested and whether they're approved or not recommended, those sort of things. So the research has already been done and it's out there. I know more continues to happen because this is a process that needs to age for a while, right?
Yeah.
It's kind of like studying a drug, right?
Sure.
You don't know when somebody takes it what the side effects are going to be. So you have to kind of take a long view of it. And that's where we are in the stage of this particular technology, is we are, starting to analyze, and that's where inquiries came in about getting cables that would work.
Yeah. And so what you're talking about there is also taking a look at the flexible and durability of the design of what you're putting together and equipment that you have.
Right.
And it's all equipment. You just can't, like you said, you just can't take any standard computer or CPU and just say, I'm going to merge this in an isotopic, dielectric liquid. It just doesn't work. So that even goes back to the manufacturing process and making sure when you're putting a system together, you're asking the right questions.
Right. I mean, in some instances, it's not necessary to, go to that level or that extent in investment. But major data centers with thousands of racks and dealing with, there's an economy of scale here where it becomes very much worth exploring this as a end solution.
Sure. Yeah. And it's one that can last quite some time too. Now, I didn't discover how long those dielectric liquids are good for? Did you find out any information on that? The
No,
length and lifetime of that?
I don't know. I think it depends on the filtration, and it depends on the materials that are leaching into it. But I believe that it's substantial.
Yeah.
From what I understand.
Well, yeah, because from what I understand with Harry's project that you've been helping them on, the question is becoming that they're having an issue with the cabling breaking down.
Right.
So that liquid's been there for some time.
Right.
And I'm not sure, like I said, of the length. Maybe Harry's on, he can let us know how long those cables were in that, immersed in that liquid before they started breaking down.
I think it was 90 days.
Was it 90 days?
Yeah, I don't think it was long. But the liquid itself, so you understand that them becoming brittle means that the material, the chemical composition of the jacket was breaking down.
Yeah.
And chemicals were leaching from the cables themselves into the liquid. Right. So I think that's the X factor, because then it's not just dielectric fluid anymore.
It changes the composition of the fluid.
Right. And so I don't know what the actual filtration process looks like to convert back into solely a dielectric fluid. But I did see, as a matter of fact, I remember now, I saw some diagrams of the process of, so the fluid is almost boiling. Okay. Yeah. And it has a lower boil.
I think we have a photo for this.
Yeah, it has a lower boiling point than water does. I think water's like 212.
Yeah.
It's a lower boiling point. But what happens is when it comes out of the tank, and one of the two phases is actually treating the steam from that, and then condensing it back like a still, right?
Sure.
Condensing it back into liquid form. And what's left, the byproduct that's left out of that is not the dielectric fluid. So it's like they're able to just process that out.
Yeah, I think we have a diagram. Can you pull up number 3, Jesse? I think we actually have a diagram is exactly what you were just explaining, so people can take a look at it. And like you said, one of the things to take a look at too is all the non-conductive materials that are needed for this.
Would you say 3?
I believe it's number 3.
The server rack diagram?
Yeah. I think that's a diagram that I had that showed exactly what, there you go. This is exactly what you're explaining with the server racks.
Right. So it recondenses it on this guy right here.
Correct. Yeah. So you kind of see both
and
phases here.
And the weather pattern is pushing in from Groundhog Day.
Yes.
So yeah, and so that's the idea. When the steam is coming through and it's recondensing, what's left over in the material that doesn't steam up is stuff that they purge, I imagine.
Yeah, I imagine it's purged out the end there, because you can see where it comes out, goes back in, and retains through the system. So this actually shows both cycles of the phases.
Okay.
So you see where you have like a phase 1 scenario.
Yep.
If you follow it all around, and then if you want a phase 2, follow both diagram, the full diagram all the way around.
Right. Good stuff.
Yeah, it's interesting,
So, I'm telling you, I mean, I have... my world has expanded since getting here and getting into this, because it wouldn't have crossed my ecosystem.
Yeah, I
in
know,
any
right?
data environment in a normal, in a normal world. But this is something that is leading edge, even though, all due respect to the 1800s, they're getting around to it now, and there are actually companies that have been in business now for almost 10 years that are in this space. And I think that now it's starting to make its way into the mainstream as discussion for options. I mean, again, there's a big paradigm shift in the brain that has to happen, that you just can't walk up to a server cabinet, open it up, and pop something in now. It's in liquid.
Yeah.
So there's learning curve, and there's an adoption.
And especially with, I'm going to throw this out there, the whole global warming phase that's going on right now. Transitioning over to this, as it actually does help environmentally speaking. I mean, the reduction of what you have as far as the energy output, and all the cooling systems and everything that goes along with it.
Fake news.
Yeah, well, it is part of the scenario.
No, I understand. So you had listed on here harsh environment cables, right?
Yeah.
And just talking about different attributes of harsh environment cables, that they need to be made of non-conductive materials. They have to have compatibility with the coolant. So we talked about that. And that's one of the challenges, is identifying because of the floor. Why am I having such a hard time with the?
I want to say fluorescence, but not.
Yeah, it's a fluorocarbon, but it's
Fluorocarbon.
Anyway.
Those technical names.
Yeah, but ester based as well, coolant. So there's a couple of different compounds or bases that are used to create those the dielectric fluid.
Yeah,
right?
well, and really, when it comes down to the fluid, I mean, I think that's probably the easiest part of the equation.
Yep.
is picking the proper fluid. Just because you're going to take a look at, okay, I'm going to put a system together. It's going to generate this much heat.
Right.
Okay, so what coolant do I have that works within that span? And then you can go and you take, like I said, an isotope type of coolant, and go with that as long as it meets the heat requirements.
Right.
And it is also not, it's going to, the thermostat, I can't even say that word, thermal requirements, as well as the electrical requirements.
Right.
And a lot of the harsh and cable environments that are being used and tested in this are the ones that we've used for, say, on oil rigging, where you do have the contact with different types of chemicals out there in that process.
Right.
Robotics, because you have a lot of movement. And, no matter what, when you put something in, you're going to have some fluid movement. And so you need something that does have some movement with it. It's
right.
not so stiff.
Right. Although I am currently working on a solution for a company that is needs cabling to use in a vacuum environment.
Okay.
And apparently these cables, they don't need to flex, okay, because of the nature of how this robot moves. It's the cables aren't moving, but they do need to withstand temperatures over 85 degrees Celsius in a vacuum, because there's no airflow in there, because there's no air.
Yeah.
Right.
So there's no movement whatsoever.
Right. So it's not unique to just the dielectric fluid immersion technology, but also in these types of environments as well.
Yeah, and it's funny you say we're talking about environments. We're kind of going off game plan a little bit here, but we used to provide cabling for the space shuttle program,
right?
And so we know that we've worked with cabling before that has been in the harsh environment of space. Now, whether it's contained within the space shuttle itself,
right?
It's still a rugged environment to be have to work in,
right?
And so we've had cabling out there in many different facets of harsh environments.
Right.
And that's just where we take that. We take the knowledge of who we work with Quab and Wire and Cable. We have had Steve Spoons on a while back.
Right.
And we can take and specifically look at a targeted harsh environment, that's out there and say, okay, we need to take a look at this particular cable that will meet the needs and satisfy the requirement for what is taking place.
Exactly. And it's you long for the simple days of just plugging something into a switch and then into a router and then into a box, right?
It's not as simple as it used to be.
No. but better. Yeah, I mean, more capacity to dissipate heat equals better computing power, across the board, because it can run things more aggressively, so more heat can be dissipated.
Yeah, and like stated before, even though a lot of this start off with using, mining of Bitcoin, AI is just going to cause this to explode.
Right.
And then we keep bringing up AI because it is an essential part of our lives now. I mean, it's something that is here. It's something that's going to grow. It's something that we're all going to have to learn to become compatible with.
Right. And I mean, if you see how fast AI responds, whether it's by creating graphics that you tell it to create or by writing a summary of something you ask it to write, it's pretty fast.
Yeah.
And it takes a lot of processing power to do that.
And that processing power equals heat.
Yes.
And that's, number one killer.
Yep.
When these
So
things.
if you want to end global warming, turn off all the computers.
That's a smart idea. We can go back to times like Little House on the Prairie.
That's it. Yep.
AI is going to solve global warming. Don't worry. Not only that, but they also we're not far off. I think they've gotten it to like -9 degrees so far. There was a group out of Korea that last summer, July, they claimed to have room temperature superconducting, which is like the holy grail, just like fusion is the holy grail of power, right?
Yeah,
right.
So we're talking about room temperature superconducting, and a bunch of people tried to peer review it. They couldn't get the same results. They found a bunch of errors, but long story short, this LK99 material, they actually did get it to about -9 Fahrenheit, which normally to do superconducting and do these types of like quantum computing and stuff like that, you have to have it almost at absolute 0 Kelvin.
Right.
So
okay.
it's massive, massive, massive progress. So hopefully within the next 5 to 10 years, we'll do genuine room temperature superconducting where we won't need cooling.
So you suspect then that this is just a momentary lapse to have dielectric cooling scenarios?
Yeah, I mean, what you guys could do now is sell this to every data center in the world. It's going to take decades for every data center to convert to this new technology.
So
of
this would be
superconducting.
a nice transition phase,
Right.
is what you're saying, yeah.
Right. We can get rid of their Cat 3 and, upgrade a little bit.
Hey, Jesse, do you know how they were able to get to that point?
For the superconducting?
Yeah.
Yeah, with AI.
That was it?
They used
AI was
AI
able to figure it out?
Yeah, so AI, not only was AI used for the modeling on how to do the actual experimentation of the superconducting, but it also created the element. The LK99 element was discovered and synthesized using artificial intelligence.
Wow.
Yeah.
That's pretty impressive.
Yeah, and that's Korea and Japan are the ones that are finally starting to do some peer reviews and get some progress on it. And then also what this is going to enable is also a lot of fusion stuff. So this is going to enable quantum computing theoretically here in the near future, to where just like this computer sits on our desk right here, we can have a quantum computer sitting there. We don't have to have this giant factory warehouse with liquid nitrogen cooling to as close to 0 as possible.
Right.
Just to do a few calculations, every 3 years or something crazy. You'd actually be able to, just like you put a stick of RAM into your computer, you'd be able to insert a quantum chip into your computer to do superconducting.
That's wild. And fusion is coming right along the side of that, too.
I'm not versed in that.
They actually had some experiments that were able to get it to succeed for momentarily, enough to create, I think they were saying, boil enough water to create enough steam to make a couple cups of coffee.
Aha.
But the amount of power it took to get there was,
Right.
But we got there.
Right.
So it's like anything else. Once we get to that point, we understand it and the knowledge starts to come along and we understand a little more and we just keep moving forward.
I'm waiting for warp power.
Warp, yeah. That'd be great.
Well, that's you guys laugh at that, but that's actually realistic for having quantum computing and having an infinite energy source, because a lot of what we need to be able to explore black holes and wormholes and do all this stuff, the math is there. It's all theoretical, obviously, but the math just requires immense amounts of power for us to do any of this stuff. Well, fusion is going to enable us to actually do some of these experiments.
Sure, and it'll enable some of that, but there's still a limit on physical ability, right? No matter what you do, they say you get towards the speed of light, you turn into light itself, right?
Well, theoretically, if you go to the speed of light, time stops.
Well, so
That's
Yeah, there is no time. So that's the thing is we would be outside of time at that point.
Right.
That if we had a way to control gravity perfectly, where our mass wasn't affected by the speed we were traveling, then going the speed of light wouldn't matter. You can go any speed you want if you could control gravity, and you can control your mass, and if you can find a way to control all of these things, which is theoretically possible with enough energy. We don't know what we could do.
No,
Right.
you're right about that. And the one key word you said there was energy, and that's all derived from the energy that we have. You have to have. That's the root of everything that we're talking about.
Right. Yep. I mean, there's enough energy in one atom to do to create a lot of energy. I mean, the bomb
exactly what
proved
they're
that,
talking
right?
about. Yeah.
Yeah. I mean, it's
But didn't Dr. Brown already create the Mr. Fusion? He used it in a DeLorean.
Emmett. Yeah.
Yeah, right?
Time travel's on its way.
17 gigawatts. Yeah. No, so yeah, the idea though is again, for our topic is just being able to facilitate all of the computing power by dissipating heat, which is generated by the energy necessary to
Do the computing that's
Right.
needed. Yeah.
Exactly. And if anybody has any experience out there with computing power, I mean, with dielectric fluids or anything like that, feel free to let us know. I don't know if this is that like, what is that on the board there? It's nothing, right? It's not like supposed to be zoomed in or anything. Okay,
No,
it's an
not that I'm
icon.
aware of.
It's an icon. Okay.
Yeah, this is just a little side icon.
Let's take a look at a few more examples. Pull up number 6.
Okay.
We got some examples of what this looks like.
Yes.
Out there in the world. But yeah, it's just one thing, and then you stop and a lot of these concepts come from the basic concept of a human being. There we go.
Right. And that's immersed in a liquid. So they're shooting through the liquid, and that's what it looks like. And you would just be going, no, but it's reality.
Yeah.
Yep. And then we want to go to the next image.
Number 7. No, this is pretty cool stuff, though, to learn about. Like I said, this will be a nice transition phase if Jesse is right with what they're developing, where we're heading to. And there you can kind of see the liquid distorts.
Right. I mean, for me, again, I mean, everything from the noise dissipation, heat dissipation, no fans at all.
Yeah.
Right. The cost of the total cost of ownership of this being maybe slightly more expensive than.
Yeah, it's a bit of a startup, but the quality of life
is
So I have a
better
question
with
though
those.
on this. What is the serviceability like? Because it doesn't seem like this would be very easy to work on.
Right. It all, it's all based on design. So in order to service this, you obviously would have to.
You'd have to drain, the liquid.
Either drain it or you'd have to be able to remove components from it in some form or fashion in order to do it. So it's not
as easy
It's not
as
your typical plug and play.
No, not
Right.
by any means. So you're absolutely right there, Jesse. This is a little more involved when it comes to serviceability of these.
But remember, these liquids are not corrosive. So they're not dangerous to human contact. It's not like you got to have a glove to work on it, right? But these are, it still requires, and there's no arcing, any electrical impulses, it squelches immediately. So there's no transmission within the liquid. You just have to pull the components out. Now, if it's a rack, well, so I'm looking at, what is this here? This mining? No.
No, I don't think this is mining. I think these are just actual servers that have been placed into
Right.
itself.
So yeah, I would just imagine that.
I wonder what the construction is too, because unless there are a certain number of seal points on these, I would imagine that all the different components that are, say, on different types of cards or motherboards or board, whatever it is, like say a seeded processor, whatever is used to seal that processor, some kind of silicone-based something, is that going to get dissolved? Do you have to use a specific kind of that? I wonder what the actual setup of this stuff would be.
You do, and all of this has to be custom built.
Right.
When you go to put these together, I think every piece of this is a custom build according to what you need for your.
Well, and I think there was some sensitivity in deciding which compounds and liquids to use in order to make it as seamless as possible. But that's where those papers come in that analyze materials that are used in the cooling, and there's probably like 10 different liquids, but they are analyzed for how they treat those components.
Yeah.
Right.
Yeah, I don't have a breakdown on those components. I was just looking to see if I had anything there, but I do not.
Right. So again, it's open source. If you were to Google immersion cooling studies, let's just say, there's a PDF that will come up, or a group that will come up that was a board or a study committee actually made up of companies like Shell, right?
Was Dell one of them?
Dell, right? And there's also all sorts of experts in different areas who tested the chemical composition or tested the chemicals against the dielectric composition and put in their recommendations. It's a grid.
Sure.
Essentially.
And like I'm reading right here really quick. So immersion cooling is compatible with various server types. Okay.
Yeah.
So the servers are compatible from what they're saying, but the hardware must be designed to withstand the immersion in the dielectric liquids.
Right.
So just a lot of custom built in these. And I don't think that there's any sort of, there might be some people out there that are building these, repetitively,
right,
that have a lot more knowledge in this area. And so there's lots, you can find companies out there that can look into that for you.
Right. You're not going to need scuba gear to go work on your server farm.
Well, that's why I have Jesse. We'll just have Jesse put on the scuba gear and jump in there and go down and take care of it. Right, Jesse?
I'm a software guy, not hardware.
Yep.
Let's pull up some more examples here. Where were we at? Number 8? See what we got there. Take a look at.
Number 8 looks like the same one we've already brought up.
Maybe number 9? Funny, I generated this on using AI, this picture.
Why is Taylor looking so crooked? Look at, she's kind of like,
hey.
She got that lean. As Bob calls it, that Detroit lean.
Detroit lean.
That's what he calls it.
Oh, here you go. So you can actually see the rack and the equipment in there and see down below.
Right.
So it's almost like these are horizontal racks sitting down into it.
Right.
As you can see there.
Yeah, those don't look like typical rack units.
No. And in this particular case here, you can see there's not a lot of that cable. You can see the cabling there next to the little rubber ducky.
Right.
Not a lot of that's actually immersed into the liquid itself.
Right. I wonder if it's related to what we're talking about with the cables breaking down.
It could be. Maybe that's the reason for that. They found a solution to avoid altogether.
Right.
And work around that. Now, this is different from liquid cooling. I mean, let's not confuse the two, right?
Right. So, yeah, liquid cooling. So, if you build a computer with liquid cool, then it's self-contained. The liquid's already in the assembly. Correct. And it just circulates and gets cooled by like a radiator and then comes back out and goes back through. And so the tubing, I think it's copper tubing, right? It pulls in the heat, which then is transferred to the liquid that and then goes to the radiator that gets the fan blowing on it. So yeah, I mean, that's liquid cooled, but immersion is a different beast altogether. Yep.
Yeah.
Yep.
Let's take a look at number 10.
The rubber ducky was a nice touch.
That guy's a little bit small there, but
There we go.
There.
Yep.
And again, this different style of tanks that they're using. You can see here these more look like a polyurethane type of style of a tank.
So there also is they make now these like portable cooling units where they're self-contained. They almost look like a storage container, right?
Yeah.
And then all the tanks are inside, and all they're doing is running from the units out. It's not like it has to be in a server farm. They have these drop in and connect in, and it's all handled outside of the plant, basically.
Yeah, we're seeing some of that too. I know we talked about doing a podcast on this maybe, but using oceanic water. And what they're doing actually now is they're building these submersives, and they're sinking them to the bottom of the ocean, like I said, like a container. And it's so cold down there, you don't have a need for any of this.
Right. Well, it's like having those server farms in northern Sweden or Netherlands or where it's super cold.
Mm-hmm.
Yep.
So, and all this kind of leads up together. I mean, it all comes back to the big circle, like Jesse was saying. At the end of the day, what's the best way to cool your system down? Right?
Give it a blizzard.
Give it a blizzard. That's right.
That's image number one.
Yeah, image number one. This is how we take care of things in Phoenix, Arizona, when we need to immerse ourselves in some cooling here,
I think it's internal.
Yeah, more internal.
I think a swimming pool would have been more accurate. That's our immersive cooling, but this is...
We'll immerse ourselves in this when it's 115 out here in a few months,
That's right.
I haven't had a blizzard in a long time.
No, it's been a while.
Everybody likes them.
Butterfinger.
Yeah.
I'm a Reese's Blizzard kind of guy.
I like the peanut butter cups, not the Reese's Pieces.
Right. No, not the pieces.
Yeah.
Over the holidays, they had one called Puppy Chow. It was
Did they
pretty
really?
awesome. I'm a Butterfinger guy with Jesse, but that Puppy Chow one was pretty awesome.
What was in it?
It's like that Puppy Chow trail mix thing that they have, like a Chex Mix chocolate, a little bit of peanut butter inside it in a blizzard. Yeah, it was pretty awesome.
That sounds good.
I didn't go to lunch today, so I'm a little hungry.
Yeah.
Yep.
But yeah, that's how we cool ourselves down here in Phoenix,
So we want, as we're doing different podcasts and whatnot, we want to look at leading edge technology. We, as you can see from the different subjects we cover, we always try and find something of interest. And I basically learned something new today too, and there's something new coming out, or it's out now, but it's clear fiber. And so for one of my customers down in Florida, she asked me to look into it, but they're like Corning makes called a clear track, and essentially it's for like housing developments, and you basically run the fiber like along the baseboard.
Okay.
Right? You can't see it. I mean, you can see it.
So thin. Yeah.
Yeah, it's not invisible, Harry. It's just but it's so small and it's clear that you can run it out in the open and not worry about it, or not be aware that it's there.
Wow.
Yeah, and so that's a new product that's coming out that I want to take a look at and see how it's rated. I asked one of our people, how is it? What's it? Is it OM4? What is it? And they didn't even know yet because they just got it released to them. So
we'll have to look that up.
Yeah, it's pretty. But so we like to talk about things that are out there, and if you have any suggestions, feel free. The chat for the live works during the live, but there's a comment section on the video afterward. Please feel free to leave comments, leave ideas. We're always open to exploring different things. We can, and we respond to questions after the podcast ends as well. So make sure that if you've got any questions or ideas, post them. If you're watching this on a replay, please post and interact with us, because we can always,
and whatever it may be, it doesn't matter. I'd like us to do one sometime on Wi-Fi. Yeah. And just talk more about that, because it came to fact, somebody the other day said something about well, we had Wi-Fi 60 years ago, and I looked it up, and the first Wi-Fi patent came out in 1974.
Okay.
So 60 years ago, maybe it was about that time frame, but
right.
So
I mean, there's so many different technologies. There are a lot of creative people out there inventing better ways to do things, more efficient ways to do things, more environmentally friendly ways to do things, which no one is against.
Sure.
Right? Always let the market drive it, but we're open.
And if you want to have some fun with Mark, just say the word global warming.
2 words.
Yeah. 2
Yeah.
words.
Global warming.
Thank you, Jesse.
Global warming.
Thank you, Jesse. Whoa. Yeah. Right? Good job, John.
I know, right? Say the word global warming.
Huh?
Say it. Say global warming.
Which one?
Both.
If I say it, there's another word that goes on the end of that. Global warming hoax.
Oh.
Yeah. Anyway.
Well,
So
we're not getting into global warming, but it's not a hoax. You just don't think the reason is the same.
Man caused.
Yeah.
I think
But it's still we're still warming.
Well,
we are. Yes.
In some parts we're warming, in some parts we're cooling. We just have more temperature stations out there than ever in life. Ever
Hottest
in
summer
history.
ever recorded.
Right. Well, ever recorded. That's 120 years. So just saying.
Well, yeah, it is what it is. So.
Yeah, it is what it is.
Yeah, we'll agree to disagree.
I hope that's not going to repeat because we're almost to summer again.
Yeah, I hope so too. That'd be way too hot.
Yeah,
Last year was brutal.
And the year before that was great.
Yeah.
And the year before that was terrible. Terrible. It was terrible.
Terrible.
Yeah.
But we always have a blizzard.
Yes.
Right. So
have a blizzard in the middle of the heat. In the middle of the heat.
So
look, we want you to like, subscribe, and share this podcast. We're glad that you're here. Sorry we got a little late start with the technical issues, but we recovered and got on a nice pitch here. We definitely will be back next Thursday at 3:00.
3:00.
Arizona time. So if you're in California, we started at 2 today, but next week we'll be at 3 for you in California.
Thank you everyone for subscribing. We're almost up to what, 40,000?
Almost at 40,000. Yeah.
Almost there.
Can you believe 40,000 people? That's a lot.
A lot.
Yep.
Yeah. Thank you.
Thank you very much. And we're going to be scheduling some guests on here, right, John?
Yeah. Hopefully we'll have some guests on from Belden Wire and Cable.
Right.
And also Hubble.
Right.
And I'm hoping to get on a special guest from the White House or a person who has previously worked in the White House in the Situation Room.
Nice.
So we can talk about the White House and technology throughout.
Right. Yeah. And I believe we've put feelers out to a couple of our customers too.
That's correct.
Yep.
And so we'll get some installers on here.
Yep.
And you know what? I'm going to put this out there. If you'd like to join us, hit us up. Give us a call. We can talk.
Look, we had a comedian on here. So, that's just really let the door wide open.
Hey. Yeah,
right?
Exactly.
And not that John's not a comedian every week, but,
Hey, believe it or
Rodney
not,
was in a different league.
Oh, yeah. He's on a league of his own.
Yep. All right, everybody. We're going to take off here now. And thank you for joining us. We hope you like our new date and time. And we hope you'll join us next Thursday at 3:00 Arizona time.
Thank you.
Thank you. Have a great day.